Hey everybody, this is 2013, or this is number 1 from the 2013 exam here. So let's take a look at this one. Now there's a lot of reading to go on in all of this, and it's basically describing what's going on in this picture here, that we move 50 meters, we get up to 17 meters per second, we've got a circular hill of radius 20 meters, and that hill's 8 meters above the ground here. But you got to be careful about skipping too much here, because there might be important information like the mass is 1,600 kilograms and that it starts from rest. Those are two really important bits of information as you start this one. So first thing here is they want us to calculate the magnitude of the acceleration right here in this first 50 meters. Well, this is probably going to be a kinematics problem, so let's look at some of the information that we have. We've got the displacement. Let me write delta x there to make it a displacement, not a position. That's 50 meters. We started from rest, so we know our initial velocity is 0 meters per second. They tell us that we get up to 17 meters per second, so that is our final velocity there, and they're looking for the acceleration. So we got three things. We're looking for a fourth. A kinematic equation should get us there, and so we just got to find the one that will get us there, and it is the fifth one here. It mentions all of these things at once. So v final squared equals v initial squared plus 2 times a times the displacement there. There is no initial velocity, so that simplifies that down, and then we're going to solve for the acceleration. So acceleration equals the final velocity squared over 2 times delta x there. So now we can simply plug into our equation here. So our final velocity was 17 meters per second. We'll square that. 2 times our displacement was 50 meters. And there we go. Now we just work that out, and you'll get about 2.89 meters per second squared. Okay, so next part here is they say calculate the time it takes for the car to reach the beginning of the hill. So this is also a kinematics question. We're just studying how things are moving in this section right here. So in this one, we know the displacement, we know the acceleration now, we still know the initial velocity, and we know the final velocity. So we know 4 things. That means we have a choice of equations to use, since we don't just know 3. In fact, you can use any of the 5 equations to solve for this except the 5th one, because the 5th one doesn't mention time. I'm going to use the 3rd one because that's just one I'm really used to, that the displacement is the initial velocity times time plus 1/2 times, whoops, not g, I'm so used to writing g, times acceleration times time squared, and there is no initial velocity, so that part drops out. Now rearrange it to solve for time. Time equals the square root of 2 times your displacement over the acceleration. We're used to this often being 2 times h over g. It's the same equation, just in that case specified for vertical motion here. All right, so now we're ready to plug in here. So 2 times our displacement is 50 meters, and then our acceleration is our answer from the previous page, 2.89 meters per second squared, and if you work that out, you'll get about 5.88 seconds depending upon where you have rounded. And remember, you can also solve this with the first equation, and with the second equation, and with the 4th equation. All of those will get you to this same answer right here. All right, so now, calculate the magnitude of net force required to accelerate the car in the first 50 meters. This one's so easy you might overlook it. Net force is simply equal to mass times acceleration. So we've got the mass, they gave it to us. It's 1,600 kilograms. And the acceleration was what we solved on the other page, 2.89 meters per second squared. And so when you work those out, you get about 4,624 newtons there. All right, now on to the free body diagram here. So on this one, they just simply want a free body diagram. Now I think on today's questions, they would put a little grid on here so that you could draw relative lengths. So on this, you should have a force up for the normal force of the hill on the car. Remember, what we are drawing is the free body diagram for when the car is right up here on top of the hill. So normal force up and force of gravity down. Now, they don't ask this particular question on here about which force is bigger, but I want us to stop and think about it for a moment. How do I know that force of gravity's got to be bigger than normal force? Well, that is because it's going in a circle from here to here, and the center of the circle is down here, so we need a net centripetal force down that way. So the net force has to be down towards the center. So force of gravity has to be bigger than normal force. And that's totally a question that you should be able to handle if they had asked it. All right, now, next part here. They say calculate the minimum speed the car must have on the top of the hill to momentarily lose contact. So imagine it like this. We are flying just up and off of the hill at the very top there. So flying up and off of the hills should look familiar. That is a uniform centripetal motion problem. And we always begin those like this. The net force is equal to mass times a centripetal acceleration here. So now let's think about what we normally do. We always say the force is towards the center, and the center is down here. So the forces towards the center are positive. The ones that point away from the center are negative. Although that's not going to matter here in just a moment, actually. So the force of gravity is towards the center minus the normal force, and that's going to be mass. So plug in for centripetal acceleration, mv squared over r. But here's the thing. If we lose contact with the road, then we are actually losing our normal force. There is no normal force because we've lost contact. So now let's plug in for Fg. So mg then is all that's left on this side is equal to mv squared over r. And our m's cancel out there. When we go to solve for that velocity then, it is simply the square root of r times g. So now we can plug in for those because we know both of those. Be careful. Look at your picture here. The radius is 20 meters, not 8 meters, it's 20. So 20 meters is our radius, 10 meters per second squared is our g, and so that gives us about 14.1 meters per second. All right, last part here. They say calculate the speed the car must have at the beginning of the hill in order to have the speed at the top of the hill. You calculate it here in part E. Now let's actually go back to this here. An important part that you might miss if you're skipping over too much and just looking at the picture is it says it accelerates when it reaches the beginning of the hill, and then once we get to the hill, it coasts with the engine off. Assumed losses due to friction are negligible. So in other words, once we get to the top of the hill here, we're just coasting up under our own momentum there. So this is kind of like, imagine that we have this situation, that we just have a ramp and we have some initial speed down here at the bottom, and then we get some final speed up there at the top at this height h. That's basically what we're solving for. What does this speed have to be to get us up to this height with this speed here? So this is a conservation of energy problem. So let's set it up. What kind of energies do we have in the beginning? We've got kinetic energy at the bottom of the hill, and then at the top of the hill, we're still moving, so we have our final kinetic energy, and we have gravitational potential energy at the top of the hill there. All right, now next step, let's plug in for each of these. So this one will be 1/2 times mass times initial velocity squared, and that's what we're looking for, the speed at the bottom of the hill. This kinetic energy is 1/2 times mass times final velocity squared. That's the speed on top of the hill, plus m, g, h there. The m's cancel out, so they're all gone. And so now let's start to solve for v0. That's what we're looking for, the velocity at the bottom of the hill. So first thing I'm going to do is to get rid of this half, I'm going to multiply this whole side by 2. So what that is going to give me, and forgive the missing square, I'm going to get rid of that in just a second. I'm going to multiply this whole side by 2. So that gets rid of the 1/2 there, and we get v final squared, plus I'm going to multiply by a 2 here, 2gh. Now really there's a square here, so to get rid of that square, I got to take the square root of each side. And so that is the initial velocity. So now what we got to do is plug in and solve here. So our final velocity on top of the hill has to be at least this, 14.1, and don't forget to square it. And then we're going to add to that, excuse me, 2 times gravity times our height. Now be careful here again. What is the height? Don't get the height and the radius confused. Our height is right here. It's this 8 meters. So that's what we plug in for the height. Then just simply do your algebra there, and your initial velocity should be roughly 19 meters per second.